Now we will talk about the discrete and the fast Fourier transforms. Considering a periodic function f of x with a period 2 pi, we can make n measurements of the given value of the function f of x at a given value of x, where the value of x goes from 0 to 2 pi at regularly spaced intervals. Uh, I mean points. So therefore we will get something like this, where we have xk is equal to 2 pi k divided by n, where k goes from 0, 1 to n minus 1. So what this is making is sampling the function f of x and these points xk. So to be more specific, we know if f of x is obviously a continuous function, it's periodic with a 2 pi period, and we make some measurements. Sum is equal to n measurements at a given interval from 0 to 2 pi, and we also know that these measurements are regularly spaced. So these points can be denoted by this function, where each point depends on the value of k and the total number of measurements we are making. So we can obtain then a vector or a list of values of x of k. So another important thing now is to determine a complex trigonometric polynomial. Trigonometric polynomial that it will be q of x, and it will be equal to the summatory from n equals 0 to n minus 1 of a specific coefficient c of n multiplied by e to the I n x of k, so that q of x can interpolate the function f of x at the xk nodes. That is, q of x k is equal to f of xk, that it will be equal to fk. So what does this mean? Well, that q of x will be in some way a how can I say it, a discrete representation of the function f of x, where we are making discrete evaluations of the value of f of x at different values of x equally or regularly spaced, so that the summatory of all these points evaluated by these values can interpolate the same or the actual value of the function f of x at that point. So we can also make another representation of this equality. We also know this equivalency, and this will be equal to the summatory from n equals 0 to n minus 1 of this coefficient c of n e to the I n x k, where k goes from 0 to n minus 1. However, we require to obtain the value of these coefficients, because everything else we already know. So we know the value of n, that goes from 0 to n minus 1, and the value of k of x of k, that will be the result of the evaluation of this previous equality here. So we can just make some algebraic operations here. Um, Multiplying by the summatory from k equals 0 to n minus 1 of e to the I mxk, we get that the summatory of from k equals 0 to n minus 1 of fk e minus I mxk is equal to the summatory from k equals 0 to n minus 1 multiplying by the summatory from n equals 0 to n minus 1 of cn e to the I n minus m x of k, that is equal to the summatory from n equals 0 to n minus 1 of the coefficients cn by the summatory from k equals 0 to n minus 1 of e to the I n minus m 2 pi k over n. That is just substitution of xk with the value that we already see. So by making just some operations here and algebraic operations, we can then conclude that the coefficients c of n are given by this operation 1 over n, the summatory from k equals 0 to n minus 1 of the function fk multiplied by the exponential of nxk, where n goes from 0 to n minus 1. So we can now obtain the values of c of n by just substituting these values that we already know. So we now know that the discrete Fourier transform of a given function f that can be represented as a vector that is equal to f0 to fn minus 1 is equal to a new vector f hat that is equal to f0 hat and goes to fn minus 1 hat, which components are f of n hat are equal to a new vector n multiplied by the coefficient vector, and it will be equal to the summatory from k equals 0 to n minus 1 of fk e to the I n xk. So there we have another representation of what a discrete Fourier transform is. Now we can also make these calculations in a vector form or notation, where the function f is equal to a new vector as m multiplied by f, where the n times n Fourier matrix Fn is equal to a matrix that of the form E and K. That is evaluating the next values, where A, E, and K is equal to E to the I n x k. It will be equal to, as I said before, E to the minus 2 pi I n k over n. That is the actual value of xk, and it will be also equal to this other value here that denotes the evolution of this exponential function. There's also another kind of transformation that is the fast Fourier transform that is actually really similar to the discrete Fourier transform that we already saw, sorry, but it has some differences. So we already know that we have the function f that goes from f0 to fn minus 1, and by the discrete Fourier transform we can obtain yet another function f hat that is equal to all the elements of the discrete Fourier transform, evaluating the functions that we saw just before. However, in a fast Fourier transform, we will, instead of having one specific vector, we'll have two vectors now. That is the even parts of the Fourier transformation that comes from f0 to f2. So not a comma, this is a vector to fn minus 2. That this will give us all the even elements of the Fourier series, transformation, and all the odd values. That's something like this to fn minus 1. And this will give us all the odd values. So the important part of the fast Fourier transform is that we can, instead of serially calculating all these elements of the Fourier transform, we can in some way evaluate these two vectors separately, allowing us to evaluate maybe both at the same time, and now allowing us to make the evaluation of the Fourier transform even faster, as we are evaluating two new vectors at the same time. So just to make a definition, the even part of the fast Fourier transform, we know that they look something like this, and minus 2, and they are equal to a new Fourier matrix Fm multiplied by Fed. That's the even parts of the original function, and something similar with the odd values. So will be fo1, fo3, up to the fon minus 1. These are transposed equal to fm f So this is actually the Fourier fast transform using the original values of the function evaluated at the specific points of the sampling. And well, another thing is just important to note that we are multiplying these elements of the original function by Fourier matrix that we already noted that it's going to be evaluated by this matrix, and each element is evaluated by this function. We just need to vary the value of xk and the value of n in order to get each element of the given matrix.